Okay, thanks. Yes, so I thank the organizer for inviting me to this workshop and for the possibility of talking today. And my talk will be a Blackboard talk, and it will focus on localization. The title is Localization. For Wilson loops in n equal to Super-Yang-Mills theory in the equal form. Is it the size of the writing? Is it okay if I keep it like that? Probably it will, as usual, it will become smaller and smaller, but I hope not too much. So, of course, I will not talk about everything about this. I will focus on a couple of instances where of application of localization for Wilson loops. So let me start with motivations. And my motivations will be very simple. In fact, localization, I see localization as a method to obtain exact results in an interacting, although quite special, quantum field theory, right? So in particular, localization can provide explicit expression for the perturbative series of certain observables. And this is, in the context of this workshop, this is a starting point for a resurgent analysis in a QFT context, okay? Moreover, in theories which admit a holographic dual, if one can resum and extrapolate to strong coupling the behavior of these observables in a suitable regime, this can give precious informations on the dual processes on the holographic dual, which typically amount to some scattering process in ADS, which is very much investigated now. So this is the motivations restricted, adapted to this context. And content of the talk. Okay, I will focus on observables which include BPS line defect. I've got observables, including a BPS line defect, a Maldacena Wilson loop. Okay. And in particular, I will focus on two issues. Okay. Two setups, let's say. First, I will concentrate, will be the first part of the talk. The second part of the talk, I hope to be able also to cover. If it take too long for the first part, we'll see. Okay. So the first part is about non-conformal. So which is much less investigated than the super conformal setups also in n equal to context. Okay. And the question that we have in this setup is the following: does localization provide still account or provide useful information for the perturbative results in flat space, in the corresponding flat space n equal to Super-Yang-Mills. This is a subtle point because the point is that localization is performed on S4 as a space-time manifold, compact S4. And when the theory is not conformal, it's not clear what happens because R4 and S4 are conformally equivalent, but if there is a conformal anomaly, it's not clear if localization still holds some information about flat space theory. Okay, this is, in my opinion, in our opinion, not yet a clear point. And we had recently a paper out with, recently last year, I think it was in November, with Luca and with a student, Alessandro Testa, about this issue. And we are now completing another paper in which go to the next order, as we will describe on these issues. See. So we do, we try to answer the question by explicit checks for the Wilson loop expectation value at low orders for the expectation value of the Wilson loop with Luca Grigolo, Alessandro Testa. And this is in, let's say, 2311.17c92 plus in preparation. So this is the first issue that I will try to cover. The second one, instead, it is in the conformal setup, and it is related to a talk that we had by Rudolf this week, and it's related to, it's in conformal setups, in particular in N equal 4, and it has to do with the integrated correlators in presence of a Wilson loop. Okay? Such observables have been already considered in a very nice work of Pufu, Rodriguez, and Wang, I think. Young, sorry. In 2305, 08297, okay, that motivated their importance because motivated the importance for the dual holographic contacts in which they correspond to scatterings in 90-day sitter of some fundamental or even PQ strings if I use SL2Z duality. Holographic image scattering of PQ strings in ADS5. To get PQ strings, they need to use SL2Z, the SL2Z duality of N equal 4, which we heard about earlier this week. Okay? Okay, however, they did this. They computed these observables from the matrix point of view, but they did not provide the measure with which these correlators have to be integrated. So they provided an expression which gives some integrated correlators of this type, but they left open the question of which exactly was the integration measure. So we try to tackle this aspect, and we also try to rephrase the integration, the matrix model computation, which was already done, in a way which is suitable for extensions to other N equal 2 superconformal field theories, and not just restricted to the case of N equal 4. Okay, so in 2308 17575 with Alberto Lerda, Mario Elisa Frau, Francesco Galvagno, we found out determinant the measure for the integration of such correlators, exploiting the superconformal symmetry, as was done for the 4-point integrated correlators. And we set up the computation in matrix model computation revisited. Okay? So this is the plan of my talk. As I said, I'm pretty sure I will be able to cover the first part. I hope also the second. We'll see. Okay, so let me start. Again, from here, are there questions up to this point? Okay. So let me start by describing briefly how localization alla Pestun provides a matrix model description of certain observables, reviewing very well-known facts for probably for all of you, but let's start with some preliminaries. So first of all, the trivial preliminaries for n equal to superior Mills theory. We have a vector multiplet. The theory contains as a vector multiplet where you have the gauge connection, a complex scalar, plus fermions, plus gauginos. Okay? And all of these are in the adjoint representation of the gauge group. We will all, in the talk, we will always take the gauge group to be SUN. Okay? And then you have hypermultiplets. It contains two complex scalar fields. You can arrange in a metric if you want, plus hyperinos. So two complex scalars. Or four real fields. Also, one of them transforms in certain representation R, and the other one in the conjugate representation R of the group. And we simply say that the hyper is in the representation R, okay? So in general, we can have this. With such content of fields in 4 dimensions, is a simple exercise to see that the beta function, which in n equal to theories in an appropriate scheme is only receives only one loop corrections, is given by as the following form: beta function is one loop only, and the coefficient beta 0 is simply the Dynkin index of the representation R of the matter divided by a pi square, okay? So you have asymptotic freedom requires that IR is smaller than n, okay? Well, this is the Dynkin index. Of the representation, and our conventions is that the fundamental is equal to 1/2. So in such a way that the index of the adjoint is n. So this is the index of the adjoint. Okay, this is our conventions. Then, of course, we can have the hypers can be massive or not. Okay. So if the hypers can have a mass, massive with mass m, and then we can have the mass can be different from 0, and in this case we have explicit breaking of conformal invariance. We can have massless hypers, but we can have the index of the representation different from n, in which case we have a breaking at the quantum level by the beta function. Or we can have a situation in which m is equal to 0 and the index is equal to n, of the matter is equal to n, and here we have in a superconformal setup. Okay? Good. Then the crucial step, a crucial step in the study of these theories was taken by Peston. Peston's approach to localization. He put the theory on S4 of radius R, and then this was also generalized to squashed sphere and so on later. Okay. Of course, doing this, one went to consider rigid supersymmetry on a curved space alla Festuccia Cyber, and to write down, so rigid SUSY on a curved space. And so there are couplings to curvature terms, and so on. Okay. Then he constructed, out of SUSY charges, he singled out a BRT charge forming forming an equivariant cohomology. Meaning that in Q square, close is not on 0, but on some bosonic generators. Including some, let's say, rotations, okay? In such a way that, okay. Then he noticed that for, let's say, BRT invariant for Q-exact observables, typically BPS observables, in the sense that they have to preserve some part of the supersymmetry. In the path integral, one can modify the path integral representing these observables, modifying the action, shifting the action into the action plus an exact term with some parameter in front, okay? Choosing appropriately without changing the value of the path integral, okay? Because everything is invariant under Q, both the shift and the observable and the measure, so nothing changes without changing the result. At this point, by choosing appropriately with a suitable view and sending t to infinity, so that, of course, it turns out, maybe typically, okay, I don't want to give the detail, but then the path integral localizes on fixed point fixed set of Q square action. And since inside Q square there are also rotation in the two planes, the action of some isometries which, as a fixed point, only have certain poles, let's say, the integral localizes to these points. Okay. And if a path integral localizes to points, then the fields become simply constant, they become matrices in the adjoint of the of the group. This is what happens. So, moreover, the saddle point approximation, which only retains the determinant of the fluctuations around the saddle point, becomes exact. Okay, saddle point, and this is the magic of localization. Approximation exact. Okay, very good. So for n equal to super Young Mills, the fixed point turns out to be as follows. Fixed locus turns out to be the following. A mu, the field A mu of x, is localized to instanton solutions k, with k equals 0 plus minus 1, and so on. Okay? And the field phi becomes a constant matrix A belonging to SUN. Okay? The fermions, of course, goes to 0 at the fixed point. Okay? So among the various observables to which this procedure can be applied, there is, of course, the partition function. For the partition function, the expression that comes out is the following. The partition function is the integral of these matrices turns out to be of minus 8 pi square over some g. Let me call it g star for a reason that will become clear later. R square, trace a square, and then a part which is due to the one loop correction, the determinant around the fixed locus. And then there is a part which is due to the instantons. Okay? And this is due to the fact that we have to sum over all these possibilities for the gauge field. This is due to the determinant around this fixed locus. See that there is here an R square, because this kind of terms arises from the couplings that you have to put to the curvature of the sphere to maintain supersymmetry on the curved space. Okay? So this is basically, this is the sum over fixed point set. It becomes the integral over a metric. Okay? Okay, these are, if you want, these are classical contributions. Contribution from the fixed point set. This is determinant, fluctuation determinant. Okay, this is the structure. And the explicit expressions are as follows. We have that Z instantons depends on A, depends on Q, and on the radius. Then most of the time I won't write all the dependencies because it becomes a bit pedantic. Will be organized as the sum over the instanton sectors, weighted by the powers of Q, of some function of A or R, which was computed by Nekrasov. These are Nekrasov partition functions. Partition function, comes out of the integration of all the moduli space of the multi-instanton solutions, right? It's a way to write down the integration, the result of the integration of the multi-instanton moduli space. Okay, and where Q star, which is e to the 2 pi I tau star, namely e to the minus 8 pi square over G Yang-Mills square plus eventually a theta term, which I will discard most of the time here, okay? This is the instanton part. And well, the Z1 loop arises a fluctuation determinant and typically is written as in terms of ratios of infinite products, okay? I don't write here for the moment the expression, I will write it later. Ratios of infinite products. So in fact, it can be divergent, okay? So this is well explained in Pestum's original work. And since this can be divergent, one has to be careful. And the situation is as follows. If the matter representation R is such that its index is equal to n, so we're in the superconformal case, so beta function is 0, these infinite products, the infinite products, can be expressed in terms of Barnes G functions. Okay? Well, actually, if the mass is different from 0, a divergent term formally remains in the partition function, but this term, which is divergent, however, is independent on the matrix A, so it cancels out in all correlators. Okay? There is a diverging but A independent factor irrelevant for correlators, cancels out. Okay. Yes. Could be related to that. Yes, probably it is. Yes, I think so. Yes, but here I'm telling to you that everything works fine in this procedure for the superconformal cases, while at the beginning I said that I was going to investigate non-conformal setups. So here we have to understand what to do in non-conformal setups. And this was, the way was already described partially already in Pestum, and then Russo and Zarembo later gave other considerations and so on. Let me, we revisited it also a bit, and let me state what one can do if the matter is not in a representation with, which is asymptotically free. So we have in an asymptotically free theories in which the index of the matter representation is less than n. How can we proceed? We suggest, Pestum originally already suggested for one particular case, we proceed by the following. We embed them in a conformal theory, in a regulator conformal set up. So with a representation R, which is in some sense contains the representation R, so we add some extra matter content, and such that the index of these representations is equal to n, okay? And you can have, sorry, I made a mistake. Okay, very nice. Oh, fuck. I think I forgot one. Okay, let me go by heart because I forgot one. Oh, fuck. Okay, yes, I forgot one part of the seminar, so let's say. So, for instance, let us suppose, and then the idea is that the extra content that you put, you take it massive. And then you can see what happens when you consider the scale, energy scales, where this massive content is very, very far away, so you don't see it anymore, and you go to your, and you flow to your non-conformal theory. So for doing this, we find convenient to refer to one particular instance. For instance, suppose that we are interested in a theory with NF time, the fundamental representation NF times, so NF fundamental flavors. Okay, in this case you have that the index is simply NF divided by 2. Okay, so if NF is less than 2n, you are in a asymptotically free theory, right? So the idea is to take then simply R star is a fundamental to the power 2n, right? So we get, in this theory, you have an extra 2n minus nf fundamentals, hypers. Okay, which we take massive with a mass m. Okay. Okay, in this situation, I'm sorry, what happens is the following, and this is a real problem because this was not so obvious. Some formulas were a bit complicated, so let me see if I'm able to remember everything. So, okay. So what happens, there are two things that happen. By looking at for in Z instantons, what happens is the following, that the contribution of the extra fields to the Z cap of Nekrasov is very simple in the limit in which M is much M is big. So let me say in another way. Now we consider energy scales E much smaller than M. Okay, and for the partition function, as well as for the Wilson loop, we'll have the only scale that we have is just the radius of the sphere. Okay, so we consider this regime. In this regime, so we have to just 1 second. I try to get the formulas from here because I don't want to write wrong things. Okay. So I should have it here already. So where is it? Is it this one? Yes. Or this one maybe? No. Fuck. Probably this one. I'm sorry, just a second. I'm a disaster. Sorry, just a second yet more. Okay, this one. Okay, it's here. I hope so. Okay. Okay, very good. Okay. Okay. Very good. So the idea is following. We have this theory, which is a regulator theory, okay? And then we look at it. So this theory is the one with 2n fundamentals. This is super conformal. And here we have the theory with only nf fundamentals. And this is the, well, as we vary the scale from m, from e close to m, or the situation in which e over m goes to 0. Okay, we are at the two extremes. We have the regulator theory and our theory. Okay. If we look at the instanton part, what happens for m in this limit? The contribution of the extra fields to the necklace of partition function is very simple. At the leading order in m, it only redefines basically in the instanton moduli space integral. Basically, what happens is that so basically zk of AR becomes the mass is redefined to the power 2n minus nf times zk. Okay? There is an extra contribution for this extra moduli that you have in presence of these extra fields. So the final result is simply that what was the parameter of the necklace of partition functions, the expansion parameter of the necklace of partition function, is this dimensionally transmuted into lambda to the 2n minus nf, right? So let's say that, okay, in such a way that lambda to the n minus nf is equal to the mass to the power 2n minus nf times q star. Okay, so in the new expansion parameter is this one. This is what you have. Okay, first thing. Second thing that happens is the following. In the one loop part, what happens is the following. Z one loop, the fluctuation determinant, has now two parts, right? A part which comes from the Z1 loop, let's say star, with the regulating theory, is Z1 loop for the theory we're interested in, okay? Times the Z1 loop for the massive multiplets, okay? And this part here is given by the product over the roots of the h function alpha dot a over e. This is what we saw in Rudolph's seminar the other day. And below you have the product over the weight of the fundamental representation of a. This is to the power nf. Okay? The problem is that to arrive at this expression from the infinite product, we have discarded some A-dependent, would have discarded some A-independent diverging factors. In fact, is to consider together this with this one, which is 1 over the product over the weights of H. This is the massive one, the massive matter, plus A plus M divided by E times H of W dot A minus M divided by E to the power 2n minus nf divided by 2, okay? Then in this case, you haven't done anything wrong in passing from the infinite the determinant expression to this expression in terms of h functions, okay? So this is, going to this as being well defined. Okay, let me remind you what are these h functions. My definition here is that this is the Barnes-G function times c to the minus. I put here this. And so this is directly the product, infinity 1 plus x squared, 1 squared to the power n, e to the minus x squared over n. Okay? So this is the definition. So this is kind of the expression that you get. Okay. Now, the point is that we want to study the decoupling limit, okay? In which m, e over m, is much smaller than 1, okay? So in this limit, if you want to study the one loop, the logarithm of this expression, one finds that using the large argument expansion of the Barnes-G function, I skip of course the details, one finds that the logarithm of this massive regulating part goes like 2n minus nf r squared, the log of mr plus subleading terms. Goes like that, okay? Therefore, sorry, times the trace of a square. So we used for this the large argument expansion of the h function, and also the fact that if we do the sum over the weights of the representation of weight times a, so this a was of course the vector containing the values of the matrix A. This is simply squared. This is simply the trace in the fundamental representation of A squared. Okay? So this is very, very clean what you do in this setup. So I think that altogether we obtain in the decoupling limit the following. Sorry for the emergency. So you get the following. You get that Z becomes the integral over the matrix, and the quadratic part has been redefined times r squared log mr trace a squared, and then z one loop for only for the square times z instantons which depends on A and lambda squared, okay? But you can recognize here that what you get as in front of the quadratic term is, this is the beta function coefficient for this theory. So this is nothing else that minus 8 pi squared over g squared of r, where this is the running coupling constant. Yes. Yes, I must have forgot something. Oh no, yes, I have forgotten something, of course, thank you very much. Yes, it was incompatible. Yeah, there was, if you look at the first expression I had, there was an r square here, okay? So this is dimension, r squared times a square is a dimension. Okay, so thank you very much. No, I leave it there, so I can absorb everything except the r square, okay? Thank you very much. So this is the running coupling of the n equal to NF theory, okay? With initial condition such that this running coupling evaluated at the scale m is what I had at the beginning in my theory, right? So G star has to be interpreted as the renormalized coupling in the field theory at scale m, okay? This is the point. So now we focus on the regime in which this scale m is much bigger than the scale we are interested in, which is 1 over r. And this is also much bigger than the dynamically generated scale lambda. In such a way, we are allowed to neglect the instanton contributions, which nevertheless we could neglect in the Toft limit, but in any case, this is a neglect. And focus on the perturbative regime, okay? This is what we do. At this point, we can proceed in this way. We have to, so we neglect this, at least for the moment. We have to concentrate on the one loop part. And we write that, look at this and we write it as an exponential of an interaction action. So we define basically an interaction action in the matrix model minus the log of Z1 loop squared, okay? Which, because of the expression that I wrote there, is simply minus the sum over the roots of the logarithm of h of alpha dot a over e plus nf times the sum over the weights of the logarithm of h of w dot a over e. Okay? It's just I took the logarithm. Okay, I write like that. And I can rewrite this as minus, no, so as plus, let me use this symbol. This is the primed trace of the log of the function a evaluated on a over e. Okay? Where I introduce this prime trace is nf times the trace in the fundamental of anything minus the trace, corresponding trace in the adjoint of the same object, right? So in the action, there will becomes the trace in the matter minus the trace in the adjoint, okay? So then we can use the expansion. At this point, we can use now the expansion of H for small arguments. For small argument. We end up with the following. S int becomes the sum. Turns out that with standard formula, in the expansion for a small argument, you get odd zeta function values, r to the 2m, and then you trade this trace in this particular combination of representation of the matrix to the 2m. So this is something like z of 3, r to the 4, trace prime over to the 4, plus, etc., etc. So there are interaction vertices. The matrix model is not Gaussian like in n equal 4, but it has interaction vertices which are of this type, which are with couplings in the front of these interaction terms, which are the odd zeta function values. Right? So this is the idea. Okay. Okay, let's just generalize this to, instead of the NF fundamentals, let's generalize it to any asymptotically free matter content. This takes 1 minute. I just write down the expression. Generic R representation. We will have this. Z will be given by the integral of the matrix e to the minus 8 pi square r square over the running coupling constant g square evaluated at r, trace a square minus s int of a. And this time 1 over g square of r, 1 over g star squared, plus beta 0, the coefficient of the, okay, and beta 0, as I remind you, was equal to the index minus n over 8 pi square. And where S int is expressed in terms of traces, trace prime of a to the 2m, where now this trace prime is equal to the trace in the representation R minus the trace in the representation adjoint. Okay, this is what you get. Okay. This for the partition function, but our interest was the Wilson loop. For the Wilson loop, the following happens. So DPS, Maldacena-Wilson loop. In the field theory, the expression is the following, is 1 over n, the trace in the fundamental, I take a fundamental Wilson loop, path order exponential of, well, in field theory, we will see we have to start with the bare coupling, integral over d tau, e a mu x dot mu, plus r over square root of 2. And there is a peculiar coupling also to the scalar fields, as we saw also the other day. This is needed in order for this expression to preserve at half of the supersymmetry. So there is a non-trivial coupling to the scalars. And this is a great circle on S4. Okay? On the fixed locus, Peston showed of the BRST action is computed by localization, becomes simply 1 over n times the trace of e to the 2 pi I a r. This was already shown in the first paper by Peston. Okay? Therefore, the vacuum expectation value of this operator can be computed in a matrix model as follows. Is equal to 1 over z integral over the matrix e to the minus 8 pi square r square over g square running trace of A square minus interaction action times this 1 over n trace to the 2 pi A. Sorry, there was no I here. Sorry, it was a mistake. R. Okay? Of course, computing this in the matrix model is much simpler than doing the computation in field theory. Okay? And there are many possible, much simpler to compute. I mean, it's a very big step in reducing this to a matrix integral. Still, it's non-trivial, but there are many approaches, many possible approaches. This matrix computation, okay? Both at finite and large n. Our group in Torino, and in Rome also at the beginning, pursued a strategy very simple, which is called, not by us, it was called by, in another paper, called the fully algebra approach, which I briefly describe because is a contribution which has been proved useful very times. So how does it go briefly? It goes as follows. For simplicity, this is not really necessary, but for simplicity, let me rescale. Rescale A into square root of g square over 8 pi square, A over R. So let's make it, so now the new R in such a way that it's a dimensional. And so the quadratic part of the action is simply e to the minus trace square. So it's just a Gaussian model with standard weight, okay? But the expansion in powers of S int in powers of e to the 2m is accompanied by an expansion in power of g. Okay, in powers of A, accompanied by expansion in G. So basically, it's like going from 1 over G square trace f mu nu to the description when you put G in the covariant derivatives. It's exactly the same. Okay. So basically, you see that, for instance, the partition function becomes some overall factors which comes from this Jacobian, okay, which will be irrelevant in all the correlators. And then you will have the integral of the new matrix, e to the minus trace of A square minus the interaction action. And you can see this as the vacuum expectation value of an operator, which is a matrix operator, which is this one, in the Gaussian model, okay? So in the end, what you need to compute are complicated, maybe expectation values in a Gaussian model. Okay? And in particular, our Wilson loop can be computed as follows, can be seen as follows. The vacuum expectation of W we compute simply as the expectation value of the minus interaction with the insertion of W normalized by the partition function. All of this in the Gaussian model, right? Okay. So now we just have to evaluate these Gaussian correlators, and there are several possible strategies to evaluate here in the Gaussian model. We do not go to the Cartan-Sage algebra, picking the measure van der Monde determinant. We remain with the integration of the fully algebra, okay? So basically, we write the matrix as, we decompose these matrices on a basis of generators of SUN. Okay? We write the flat metric, use a flat matrix, in which we integrate over all these A, normalized, in such a way that if you take in this matrix model the correlator of two of these components, you simply get a trivial propagator. Okay? This is another possibility to do this. Okay. Now, in most of the cases we are interested in, the operators that we want to, or which we want to take the expectation value, are gauge invariant operators, which can be expressed in the end in terms of traces. Okay? So we will have to evaluate with this formalism correlators of traces. Okay? For gauge invariant observables, which we have to have, in the end, so expressible in the matrix model in terms of traces, then the typical observables we need to evaluate. It's just a combinatory product if you want. Let me define it like this. Are the value of expectation values of things like the trace of a to the power k1 up to the trace, multi-traces. Okay? Then the fact which is very useful from the computational point of view is that these correlators satisfy some powerful recursion relations. There are powerful recursion relations which arise which come out from the so-called fusion identities in SUN traces, which are, for instance, let me just write one of the two, like, for instance, if you have the trace of TB, some matrix, another generator summed over B2, and this is the fundamental trace, this becomes simply the trace, that is a factor of 1/2, the trace without the generators. No, sorry. We split the part where this is split, -1 over 2n times the trace of B1, B2. And there is a similar one where you start with a split trace and you fuse it. Okay? And this relates operators with lower number of distinct traces, but with higher, and so gives a set of recursion relation, which is computationally extremely powerful. So you get very quickly to high orders in computing this. So this is the kind of computational strategy that we have been pursuing. And this method is very efficient computationally at finite n. But it's efficient in large n when there are also other competing methods. Because it tells us because these recursion relations simplify, and you can really resum typically the expressions. And so this is very efficient also in that regime. Okay. In any case, at low orders, I introduced this method because if I have time, we will say something later again. At the moment, for the work with Luca and Alessandro, this is a bit irrelevant because at low orders it's very easy to do the integration in the matrix model. So in any case, one gets rather easily one gets that the vacuum expectation value is, with this technology, is the vacuum expectation value that you would have in the Gaussian model, okay? Plus the first correction that you get is g squared over 8 pi squared z of 3, and then you have g squared, sorry, I write it like this, but you see why. And then you have take the correlator of trace a squared times the trace primed of a to the 4th in the Gaussian theory, plus order of g to the 8th, where you see that you have just to take a correlator in a Gaussian model, where this part comes from the first contribution that you have in the interaction action, is the interaction vertex. And this one comes from the expansion, the lowest order possible expansion of the Wilson loop, with two lines inserting on the Wilson loop, okay? So the first one is just the one that with the Gaussian matrix, just formally the same as n equal form, same as in n equal 4, but important, very important, with the running coupling constant in it, but in terms of G of R, running as in the n equal 2, okay? Very good. And so this part, W0, is well known as a very famous computation a long time ago by Drucker and Gross, and then Eric Semenov Zaremba, so it's very well known, can be written in terms of Laguerre polynomial, okay? And at low orders, it goes like this. W0 is 1 plus G4 over, this is the Casimir, the fundamental representation, n square minus 1 over 2n Casimir in the fundamental representation. And then there is plus G4 over to the 2 CF times 2n square minus 3 divided by 2n. I mean, this is well known, it is encoded in Lagrange. And this is a contribution like you have a single line going attached to the Wilson loop. This is the one where you have ladder diagrams, two ladder diagrams, and so on. So the result is that in equal 4, everything is given by ladder diagrams. This is a famous result that actually led to the matrix model description. It has a simple formal algebra in terms of a Bessel function I1. Yes, it's even simpler at large n. Okay, now let's go to the question that I had at the beginning, right? So I'm already over, yes. So I think I will finish soon with this. So the question is, this was derived on S4. Localization was done on S4. Okay. Does it encode the resulting flat space? Okay. So this is the question that I had at the beginning, right? Now we are in a situation where there is no conformal symmetry, but it's only broken by beta function effect, okay? So this is what we are investigating with Luca and Alessandro. The situation is the following. The situation is the following. We are trying to do a check at low orders with field theory on R4, okay? And the question is that, of course, we find that it's clearly conceivable, and we find that this is true, that all the diagrams which are repackaged by the matrix model in terms of the running coupling constant, okay, actually arise in the field theory from contain logarithmic terms which are due to ultraviolet effects in the theory. So it's quite conceivable they do not distinguish between S4 and R4, okay? Coming from ultraviolet effects and should not distinguish. And in fact, we find that this is true. So the fact that everything is repackaged into this way comes out nicely and the coefficient match. Okay, so this is okay. Yes. Up to g to the 6th. G to the 6th, which you can call it 3 loops or 2 loops plus the extra integration over the contour, depending on. Okay, so this is okay. But the delicate terms, of course, are those of order g to the 6th proportional to Z3. These are more delicate because can I still take 10 minutes? I know, I'm sorry, I'm terrible. I know that I always go over. But I'm really basically done. Because instead, order G6 proportional to Z3. These are more interesting and more delicate ones. Because in the matrix model, we have this following. Matrix model, we have G6 Z03, trace A square, trace prime e to the 4th, which goes like G6 Z03, and then there are 2 terms. I mean, when you do the weak contraction here, basically you have a vertex from here, and you can contract it in 2 ways. You have a vertex, which is like this, which brings us Z3 here, and then you could go to the Wilson loop like this, with this, and this one contract by itself in this order, okay? So this gives you something like the trace, like TA, TB, TA, TB, which has a certain color factors, which depends on the representation, right? And then you have another possibility where you contract instead this and this with its own loop, and this one contract by itself. So there are 2, it gives you immediately a Casimir. And so you get actually here 4 CF n squared times the beta function coefficient. So this part here is present also in the superconformal case, and it's already been checked, and it works, okay? Also in the superconformal case, and it works, okay? For any representation. This one is the dangerous one, because you see, this one is proportional to the beta function coefficient. So it could encode an anomaly in the sense that we could do the computation in field theory and reconstruct such a term with a different coefficient. Okay, this is possible that because sphere and R4 are not completely equivalent anymore, I could in field theory recover something like this, but with a different coefficient. So it's very delicate, this one. Our results, we finally have apparently finished all the computations and all the diagrams, indicate that actually it is not the case. So we get the same coefficient. This is dangerous, but we do get the same coefficient. I don't go in the details, but let me state that, however, the computations are absolutely non-trivial because, first of all, there is a nice thing that to compute efficiently the diagrams in the field theory, it's convenient to organize them in the so-called difference theory. And when you take for granted the result of n equal 4, and then you write, just look at the difference with this theory, which basically amounts to realize in the Feynman diagrams this principle of the trace prime. So you have a contribution, whenever you have a contribution from the loop, an internal loop, basically the diagrams are organized like this. Whenever you have a certain loop, a diagram could be with the gluons or scalars, and then you have a loop in the representation R over some field with loops running the representation R. You automatically, by the fact that you have expressed some diagrams in n equal 4 using the effect that you automatically get the same diagrams with something running, with the analogous fields running in the adjoint representation here. And this is exactly this trace prime structure. So it's convenient to organize the diagrams in this way. But, and this is good, but this is not enough. This is the last thing I write down. There is a very subtle effect, namely that, for instance, I order G to the 4, okay? I order G to the 4, you would have a diagram like this, okay? And n equal 4, in n equal 4, this diagram is equal to the diagram with a loop in the adjoint hypermultiplet, okay, with a minus sign, because there's some cancel. This is what's stated in n equal 4, okay? And so you can trade this for this, and you get this trace prime structure. But this is exactly true in D equal 4, which in n equal 4, you never care about the fact that you can go out with dimensional regularization, because the theory is fine for this. I mean, you can for these observables. So, however, the truth is this is not exactly equal to this, but it's D minus 4 times some evanescent terms, okay? And therefore, the evanescent parts of this one, okay, when you replace the bare coupling into the running, or the normalized coupling, okay, this gives you, this is a contribution to, this one, okay? This would be G bare to the 4th, right? So this will not compete with diagrams such as this one, for instance. Okay, this would be G to the 6th, where here something is running. This would be G to the 6th, and this will give a Z3. This contributes to the Z3 part, a two-loop bubble. This one would never contribute to this, except that you have to replace this G to the 4 with the renormalized coupling, because in order to cancel the poles, however, at this point, in this evanescent part, you get some extra G to the 6 contribution, okay? Because the pole is canceled, okay? Because this is poles. Okay, but you still say, well, there is no Z3 here, so in any case, you cannot correct this coefficient. But there is still a very non-trivial integration to do over the Wilson loop contour. And apparently, in a very miraculous way, the integration of the kind of function that you get in the evanescent terms over the Wilson loop, actually they do produce a Z3, okay? A very non-trivial integration produces Z3 and goes to change, contributes to the coefficient of the Z3. And only if you take into account all the contribution at lower orders of the evanescent terms, then you can state that this is my Z3 coefficient, and apparently this one is the one predicted by the matrix model, who somehow even knows about the evanescent terms, which I really don't understand how it's possible, honestly, but this seems to be the result. So this is the end of my talk. This is what I wanted to convey. So the part about integrated correlators, it's on the archives. Okay, that's good. Okay. So at large n, from the matrix model point of view, it's not a problem to write down the expressions. It's not a problem. I don't know if I'm able to, from field theory to, well, the problem is, I think the question is, what can you see from field theory in that limit? I must say, well, I haven't thought about it. We haven't thought about it. It's an interesting question, though. It's true. Yes. 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 Yeah. Well, I mean, at large N for field theory, we could concentrate on planar diagrams. So we haven't thought especially what simplification this brings to the computation. I said, but this is a good suggestion. No, 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 no. I think the normal, no conformal case, no. Yeah, yeah. I think not much is known for the non-conformal case. Yes, 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 yes. Yeah, 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 yes, 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 yes. It's a very simple model because it's very close to n equal 4. Yeah, yeah. Uh-huh. We should take a look. Yeah, yeah. The, yeah, still there is the fact that not to be, I mean, our result at the moment is just a specific result of a certain order. I mean, this is certainly not a proof at all order that they do agree. It would be nice to understand if we thought honestly at the beginning when we began the project thinking of finding a disagreement and that this could give some kind of hints about the form of the disagreement. So this was not, so at the moment we find this rather surprising result, but it's a possible result, it's a possible outcome. And it doesn't mean that order G to the 8, there will be a disagreement. But I think doing the computation order G to the 8 is really difficult. So I don't know if the result maybe is not so important, but still we find it nice. Also, the way in which the various type of contribution conspire is very interesting. And from the technical point of view, I must say the Lucas student Alessandro carried out this integration over Wilson loop in ways which are basically new, most of them, as far as we know. Yeah. Yes. And from the technical point of view, the integration over the Wilson loop. Yeah, yeah. Yes. Yes, yes, yes. Yes, yes, yes. There could be exactly in this kind of terms. Yes. Yeah, yes, yes. Yes. Often there are loop on loop effect often. Yes, yes. Yeah. Yeah. Yes. Yeah, 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 yeah. Right, right. That was the idea. So if you can, the point is that, yeah, 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 yes. Yes, and this is the idea that if you can trust the matrix model predictions also in non-conformal cases, it could be a starting. You could get easily at that point with the technologies I tried to describe. You could easily get results, very high orders in perturbation theory, maybe even sum them, and that would be the starting point of a resurgent analysis in a QFT, but even a non-conformal one. So it would be very interesting. Zeta 5. No, you get Z5, and then the next order, I think that should be Z7 and Z3 squared, if I remember, probably. Yeah. Yeah. Yes. This, from the mathematics point of view, is very clear. I mean, because you can bring down the interaction action many times, no? So at the next order, you can bring down twice the Z3 vertex. So certainly you will have the Z3 square, but you can also bring down a Z7 vertex. So this is, for the matrix model, it's very simple to from the field theory point of view, it's a mess. I mean, it's really a mess. And apparently there are these peculiar, the fact that you at each order you get also the contribution from the renormalization of the previous order diagrams, which for the Wilson loop they have to be integrated, and so well it's complicated, but the result we think the result is interesting, and well that's all I can say at the moment. Okay. Yeah. Yes. Yes. And yes. 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 Maybe it would even be it would even be closer to what you do in the Peston approach to use a mass mass regulator, because that's what you do in the end in Peston's treatment. So maybe it's, I don't know whether how the integrals become. This is not clear to me. Dimensional regularization, in the end, we found ways to do these integrals. So it's all the point is okay. Yeah. Yeah. By the way, of course we have to choose a scheme. Of course we have to choose a scheme to have perfect agreement. But we choose a scheme at G to the fourth. Uh, yes. So it matches. So it seems consistent. So yeah, 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 yeah. Yes, yes. Yeah, right. Exactly. Yeah, yes, exactly. This is very interesting. Of course, this is one of the motivations. Honestly, yes, we still don't know because, well, okay, no, we still don't know. Very few known. Very few classes, very few classes. Very special cases, and so if non-conformal cases, I don't know. Probably it's possible, but I don't know exactly how. I mean, but then it's just holography, and certainly no longer a DSCFT because you don't have the conformal factors. So I don't know exactly what. There are other manifolds. There are other manifolds. Yes. Yes. Enhancements and these kind of things. Yes. Yes. Yeah. Yes. Are there n equal pure n equal 2 examples? Yeah. See, maybe in some regimes. Yeah. Yeah. Mm. Okay, thank you very much. Okay, good. So this is the end of